Okay, so fibrations of generalized categorical structures and substructural logics. Nicolas Blanco from University of Birmingham. Thank you.
Yeah, thank you for the introduction, and thank you for the organizer of this conference. So yeah, it's a really nice conference, and yeah, I like the idea of having research students interact with each other. It's really nice. Okay, so today we'll be talking about substructural logic and how to use fibration to understand those. But I will focus in this talk on a really simple example where the substructural logic is intuitionistic multiplicative linear logic, and the generalized categorical structure that we'll consider are multicategories. This is something that already existed. It's not some new work. And what I did in my PhD, or at least for the first 2 years of my PhD, was to extend that from intuitionistic multiplicative linear logic to classical multiplicative linear logic by considering polycategories. And so if you want to know more about this, you can go on my website, or there is a paper that has been published in MFPS about this thing. But yeah, today I will talk to you about intuitionistic multiplicative linear logic. So I will give first an introduction to it. Then I will talk about some specific models. And from there, you could just forget about intuitionistic multiplicative linear logic if you don't know about it, and just think categorically and think about symmetric Monoidal closed category. So even if you don't know anything about logic, if you know what Monoidal categories or Monoidal closed categories, you can still follow this talk. And after that, I will explain how to represent symmetric Monoidal closed category using multicategories, and how to use then fibration of multicategories to make it clear how to refine some model of the logic. And so this builds on several work. So first, as I said, so intuitionistic multiplicative linear logic, the idea is that you have a conjunction that we call the Tensor product. We have a true value true that we call 1, and an implication that we call the implication, or linear implication sometimes. And this can be always modeled in a symmetric Monoidal closed category, where the Monoidal structure gives you the interpretation of the tensor and of the true value true, and the internal home gives you the implication. And so from now on, when I am talking about intuitionistic multiplicative linear logic, or the model of this, you can just think symmetric Monoidal closed category. And there is an old idea that is from Lambeck in the late 60s, that is logic, so intuitionistic logic in general, not necessarily linear, but intuitionistic logic, can be interpreted in what is called a multicategory, where the idea is that a multicategory has a notion of multimap, where you have multiple inputs and one output, instead of a morphism where you have just one input and one output. And the point is that this is really a good setting to look at intuitionistic multiplicative linear logic, because all of the connective there, the conjunction, the implication, can be defined by universal properties. While in a category, so it's defined by some structure, some Monoidal structure that you put on it. Then there is another line of work that goes back to Claudio Armida in the early 90s, where he observed that there are different analogies between multicategories and fibered categories. And to make this precise, he introduced the notion of fibration of multicategory. And in particular, he introduced fibration of multicategory and proved that Monoidal categories are in correspondence with multicategories that are fibered over one. So that this notion of fibration let us understand Monoidal, or offer a different presentation to Monoidal category. And this can be extended to a bifibration of multicategories, and we get a Monoidal closed category from that. So this is what I will try to explain to you today, how multicategories can be a way to understand Monoidal category, and how fibration of multicategories also give you another tool to study these things. And so to do that, I will start by looking at very specific models of multiplicative linear logic, which are vector spaces. And so the name linear logic comes partly from the fact that one of the most well-known model is a vector space, and vector space of really a nice model. And so to do that, we need to prove that vector spaces are to put a monoidal structure, a monoidal closed structure on vector spaces. So just for things to be more convenient, I will consider finite dimensional vector space, but most of the talk can be lifted to infinite dimensional or to arbitrary vector space. And the idea is that we want to define what is a tensor product of two vector space. And to do that, we take the free vector space on the project. And then we want this to be linear in each variable. So we quotient by some relation, so like some equivalent relation. And then adding this notion of tensor product, we want to prove that it gives a monoidal structure on vector space. And also we want to prove that this also define a closure, a monoidal closed structure. So we want to prove that the tensor product is left adjoint to a linear space, where this linear space is a vector space of all the linear maps. And in particular, using this last point, we can prove that any map, so any linear map from V tensor W into X, so it's the same thing as a map from V into linear maps from W into X, which is the same thing as a bilinear map from VW into X. And so we get a correspondence between a linear map out of the tensor product and bilinear map out of VW. And there is a second model that is interesting for this talk, and it uses finite dimensional Banach spaces. So you just put a norm on your vector space. And the map that you will consider are called short linear map or contractive linear maps. And so there are the map that have this property for any x, the image, so the norm of the image is less or equal than the norm of the antecedent. So another way of thinking of this is saying if x is of norm lesser than 1, so if it's a subunit, then its image will also be a subunit, or f respect unit ball if you want. And so there is a notion of norm there is several notions of norm that you can put on the tensor product. And one will be of interest for us, which is a projective crossnorm. So it's defined in this way. So the definition doesn't really matter. What matters is that it gives us a monoidal structure on Banach spaces and contractive map. So if we equip the tensor product with this norm, this will give us a tensor product of Banach spaces. And it will be a tensor product of Banach spaces that will be left adjoint to linear spaces. Linear spaces, where the norm I'm taking is the functional norm. And so all of this gives us a symmetric monoidal closed category, where now the object are Banach spaces and the map are contractive maps. But really, when we build both this symmetric monoidal closed category, and especially for building vector space, we have a lot of work to do because we need to define what is a tensor product, like this explicit definition of the tensor product, and then prove that it has all this nice property, that it is associative, that it plays well with the linear onset and things like that. But there is another way of defining vector space in a tensor product of vector space, which is by the universal property. And so the universal property states that given two vector space, we get a bilinear map from those into their tensor product in such a way that any bilinear map that goes from VW, so out of VW, will factorize uniquely through this map. And so this is saying any bilinear map will give rise to a unique linear map from the tensor product in such a way that this factorization property holds. And so using this universal property, we can prove quite easily that we get a symmetric monoidal closed category with this notion of tensor product. And the idea will be, is there a way to generalize that? And so if we can define easily what is a bilinear map, can we infer from that what should be the notion of monoidal structure or the notion of tensor product in our category? And so to do that generally, we need to have access to this notion of multilinear map, or to notion of map with multiple inputs. which is not the case in a category. A category just see maps that has one object in the domain and one object in the codomain. So this is why we want to go to this notion of multi-categories. Well, a multi-category is really a structure that is similar to a category, except that it does know about multimaps. So it has, instead of having a morphism from a domain to a codomain, it has a morphism that goes from a finite list of objects. So the domain can be a finite list instead of just one object. And then it has identity, composition, and what you would expect from them, unitality, associativity, and all this. And so in any multi-category, we can now define a notion of tensor project in exactly the same way that we did for tensor project of vector space by a universal property. So there we give a definition that is a little bit more general, because we want to give a definition of tensor project that is unbiased. So where we define tensor project of n inputs instead of defining a binary tensor project and then prove some associativity results. And so a tensor project in a multi-category. So given a finite list, we talk the tensor project is an object that comes with a map into it, such that any map that has A1 through AN in the domain will uniquely factor through it. So this is exactly the same kind of universal property that we get for tensor project of vector space. And so this can also be represented graphically like that, where we will read things from left to right. And this is saying if I have this big box there, which is a map, a multimap with multiple inputs and one outputs, such that we have A1 through AN in the inputs, we can factor it through the tensor project and get a map where this is replaced by that tensor project. And so any monoidal category will give rise to a representable multi-category by just saying multimaps or morphism that goes from the tensor project of the input. So we are defining a multimap to just be something out of the tensor project. And what is interesting is that this characterizes all the representable multi-category. So if you give me a multi-category and you say I have all tensor projects in them, then from that I can define a monoidal category in such a way that it will be the multi-category will be its underlying multi-category. And so this means that we really have two faces of the same kind, or two different notions. One, which is a monoidal category, where you give as data what is a tensor project, you give this monoidal structure, and from that you can infer what are multimaps. Or the other one, that is a multi-category, where you give as data the notion of multimap, and from that you can define a notion of tensor project. And so in the case of vector space, it's easier to take this second approach, because it's easy to define what is a multilinear map, but the tensor project is not really easy to define. And so we could try to do the same thing for Banach spaces and say, I will define what is a multimap of Banach spaces, a short multilinear map. And from that, deduce what is a tensor project. So deduce the right norm from that. And so this is what we are doing there. We are saying a multilinear map is short or is contractive if it has this property, which is just the same property as for linear map. So it's saying that it will respect the unit ball, or it will send a subunit into a subunit. So it's say if I take many inputs like that I will feed F2, I want the norm of the image to be lesser or equal to the product of all the norms of my inputs. And so in particular, if all of the x's there are of norm lesser than 1, then this thing should be of norm lesser than 1. And this defines a multi-category, and this multi-category is representable, where the tensor project is given by tensor project of object and projective crossnorm. And so this lets us know that projective crossnorm are the right notion of norm for the tensor project, and it defines it uniquely. But it still asks us to kind of give you this notion, or define this notion of projective crossnorm. So using this definition. and prove that that it is a tensor project. And this is not really clear why this will be the tensor project, but there is some property of the crossnorm, of this projective crossnorm, which is it's the greatest norm that you can put on the tensor project. So among all the norm that you, or at least all the well-behaved norm that you could be putting on the tensor project, it's the greatest one. And so the question will be, is this property, the fact that it is the greatest one, connected to the fact that it is the right norm for the tensor project? And indeed it is, and it gives us a way to understand better why we want this norm on the tensor project of Banach space. And so to do that, we start with the universal property of the tensor project of vector space, so this factorization property. And we say, let's start with a norm on A and a norm on B. And what I want to compute is a norm on the tensor project, and it should be a tensor of Banach space. So it should have a short bilinear map there in such a way that it will factor any short bilinear map. So we want to kind of take this property, this factorization property in vector space, and lift it to the same property in Banach spaces. And so if you are familiar with Fibration, there you should recognize the notion of up-Cartesian map. And so this is really saying that this map into the tensor norm is up-Cartesian. And so to go back a little, I'm saying if I have norms on my domain, I want to find an object that will come with an up-Cartesian map. So I want to find the push forward that will come with the up-Cartesian lifting. And so this is the reason why we want to introduce notion of up-Cartesian maps and the notion of up-Fibration of multicategories. So then if I have a functor between multicategories and the base one as tensor, if the functor is an up-Fibration, I can get tensor in the top one by just taking the push forward of the tensor project, so along this map. And just if we take this factorization property and the specific case where this thing is an identity, this is saying that I want for any norm on A tensor B, I want that the identity is lifted to a short map there. So we want the identity to be short. And saying that the identity is short or is contractive is just saying that the norm that we have there is less or equal to the norm of the tensor project. And so this is exactly the property of the projective crossnorm, but it is the greatest one. So yeah, in order to do that, we define up-Fibration of multicategories. So it's a little scary, but really it's exactly the same definition as in categories, except that there is some bookkeeping to do because we have multiple inputs. But really saying phi is up-Cartesian if any psi that lies over factorization by f, the image of phi, then will uniquely factor through phi. And so this can be represented graphically like that. And now an up-Cartesian, an up-Fibration is something that has all up-Cartesian map, or all up-Cartesian lifting. So it's saying if I have a multimap in my base category, and I have object over all the object of the domain of my multimap, I should be able to take their push forward. So an object over B that come with an up-Cartesian map. And so in particular, if I'm taking the push forward along the tensor map, so the one that goes from AB into A tensor B, I will get a tensor over there. And so what I did for Banach space and vector space can be done for any multi-category. And we can prove that a multi-category up-fibered over a representable one is representable. So if I have an up-fibration, tensor in the base, then I get tensor on top. And so yeah, in particular, so this is the representation of the factorization property of universal multimap. So we can tensor the input. This is the universal property of up-Cartesian multimap. And we see that this really looks like this one, except that it is kind of parametrized by this functor P. So this property, factorization property, should hold only if it's already true in the base. But if we take the base to have no information at all, So if you take the base to be the terminal multi-category, then there the factorization property will hold automatically. So we will everything will factorize every time, and so this will say that this is a universal multimap, because it should always, this factorization property should always should hold in any case. And so this gives this theorem that in particular category as all tensor, or a multi-category as all tensor is representable if and only if it's bifibered over the terminal one. And so in this talk, I focused on the tensor project, but something similar can be done for implication. So we can define a notion of internal home in a multi-category, and we can prove that internal homes corresponds to pullback, to pull back along a functor. And in particular, we have that Monoidal clause categories correspond to multi-categories bifibered over one. So we can get all model of EMLL in this way. So yeah, to conclude, so in this talk I gave different approaches or different ways to model intrinsic multiplicative linear logic. So the usual one, which is by using some structure that you put on a category, namely a monoidal clause category, so monoidal structure. The second one is as some universal property in a multi-category, so saying that we can characterize tensor project as universally, as having a universal property in there. A third one, which is as a fibrational property, so saying that they are the tensor project or the in a multi-category are push forward, really, or defined by push forward. And so this let us, for example, lift models from a simple multi-category into a more complex one, like we did with vector space, from vector space to Banach spaces. And there is another one that I didn't really discuss, which is as structure object. So it is known that pseudo-monoid in CAT are equivalent to monoidal categories. If we take residuated pseudo-monoid, we get monoidal clause categories. And so this is another approach to this kind of model by saying that they are interpreted as a residuated pseudo-monoid in CAT. And so this last thing can be related to the other by some multi-categorical Grothendieck construction. So this is a generalization of the Grothendieck construction in the multi-categorical case. And in particular, using that, we can prove a correspondence between monoidal category as pseudo-monoid in CAT and model categories as multi-category of fibered over one. And then we can play this game with things more complex. So instead of intuitionistic multiplicative linear logic, we can go to classical one by looking at polycategories, where now the map have multiple inputs, but also multiple outputs. And so this is what I did in the beginning of my PhD. But you can also play that with maps that have other shapes. So for example, if you take Cartesian multi-category, you get a model of intuitionistic calculus, so intuitionistic logic, not necessarily linear. And that will be all for me. So thank you for listening.
Thank you. Let's clap.